One of the things we get from the approximation that a fluid's density is constant is Pascal's principle. And to see what this means, we can imagine we have a fluid-filled cylinder. We're going to make it horizontal so we don't have to worry about pressure variations with depth. And we've got pistons inside the cylinder. So we've got a little piston here in the small end that can push fluid in, and this big piston here at the larger end can also push fluid in. If we have a force F2 that pushes on the small piston that has an area A2, that force is going to be transmitted through the fluid since it can't be compressed, and it's going to act on this larger area A1. This piston is going to have to move because if the fluid can't be compressed, the little piston is going to push some of it out of the small tube, and it's got to go somewhere, so the big piston will have to move. The pressure at the small cylinder, by definition, is F2 over A2. So that's P2. However, the pressure is the same throughout the tube, again ignoring the small horizontal variation that we don't care about. And if it's going to be the same throughout the tube, that means P1 equals P2. But again, by definition, P1 is F1 divided by A1. We can solve this plugging in what we know about these two pressures and the fact that we know they're equal. And we get that the force on the large piston is F2 times A1 over A2. Now, if we imagine the large piston has 100 times the area of the small piston, we can put a very small force of 10 newtons on the small piston, and we get a very large force of 1,000 newtons on the large piston. This is the reason why you can use a hydraulic jack to lift up your car without having to be the Incredible Hulk. Just a small amount of force will let you lift up one corner of your car. Now, what's also interesting is to see how far the large piston moves if the small piston moves a distance d2. If we use incompressibility of the fluid, we can say the volume of the fluid pushed out of the little tube by the little piston has to be A2 times d2. The large piston has to move enough to accommodate that same amount of fluid, so that would be A1 times d1. That must be equal to A2 times d2. We solve this for d1, and what we see is, just as the force was multiplied by a very large amount, the distance will be divided by a very large amount. So the large piston moves only a tiny distance when the small piston moves a lot. So when we go back to jacking up the car, you have to move the handle up and down over 50, 60, 70 centimeters, and the car will lift up by 1 centimeter or less. You have to do it over and over again. The reason this is the case is we can't get something for nothing. We have to have conservation of energy because that fluid is not a source of energy in itself. We have to have F1 times D1, which is the work done by the large piston, equals F2 times D2, the work done by the small piston. When we plug in what we've already found for F1 and D1, we get that this is obviously true. In this sense, the water or the hydraulic fluid is acting like a liquid lever. Now, in reality, there would be a little bit of energy loss here as the fluid heats up. There is some friction associated with it, but we're going to ignore that. And for our purposes, we can use this conservation of energy here. This explains how hydraulic machinery, the big construction equipment that you've seen driving around on construction sites, you notice it's generally painted and covered in mud, except there's always a shiny silver cylinder. And this is the hydraulic part that's doing the actual work. This also explains why, if you've ever done anything with your car's brake system other than change the pads, you have to bleed the brakes, which is get the air out of them. If you don't, imagine that you have air bubbles in this piston, and then you push down here, which represents your foot on the brake pedal. Those air bubbles are going to get much smaller, and when they do that, they'll make room for this fluid, and the big piston doesn't have to move at all, which means the brakes themselves won't engage. So it's very important to get the air out of there. This increase in pressure with depth that we talked about before also has an interesting effect on objects in the fluid. The pressure on the bottom is larger than the pressure on the top because of this height difference. We know that the pressure down here, since it's rho GH, will be larger than the pressure up here at the top. So we can imagine walling off a little cube of water in this big tank of water, and we'll give it a side length of S, and we look at all the forces that act on it. We've got pressures on the left and right face and the front and rear face, but we don't care about those because by symmetry they have to balance exactly. All we care about are the top face and the bottom face. So on the top face, our pressure P top is atmospheric plus rho gh, since h is the depth of the top face. On the bottom, we've got P bot, which is atmospheric plus rho g times this larger height, h plus s. If we multiply these by the area, we get the forces on the top and bottom, and we can see that the difference between the top force and the bottom force is just rho g s cubed. This is rho g times the volume of the cube. In this case, that exactly balances the weight of the cube of water, and that's why it's stationary. As a general rule, though, we can call this difference in pressure creating a force, we can call that the buoyant force, FB. And we say that it's equal to density of the fluid times g times the volume displaced. If this is greater than the object's weight, which is density of the object times g times its total volume, we see that it floats. We can figure out what fraction of the object will be underwater if we know its density. Now, if we did some complicated geometry like a person, we'd have a very hard time doing this problem, but we'll use a cylindrical, or rather rectangular solid, so that we have a uniform cross-section. It's the same all the way up and down. So we'll say the cross-sectional area is A, the height is h, and the depth underwater is x. The submerged part, that's the displaced volume. That's got to be A times x. If this is in equilibrium, if it's just sitting here peacefully, buoyancy and the weight force must balance. So we get that the buoyant force, which is m times g, or rather the buoyant force must equal m times g. So the buoyant force, which is density of the fluid times g times the volume displaced, equals density of the object times g times the total volume in the air and in the water. So on the left, density of the fluid times g times a times x, the portion underwater. On the right, density of the object times g times a times h, the full height of the object. We can cancel the area and the gravity to get this expression, and what this tells us is the fraction of the object submerged, x divided by h, is density of the object divided by density of the fluid. This tells us for something like ice, which has a density of 917 kilograms per cubic meter in water, we get that it's 91.7% submerged. This is the reason why you've heard 90% of an iceberg is below the surface of the water. It's because of this fraction. Now, after seeing this, you may think only things with densities less than water can float. But in fact, we can make ships out of steel or lead or whatever you want, as long as you wrap that metal around a large balloon of air. The total density, the net density of the ship has to be less than water's density, but the individual parts could be more dense. This force is also still present even if the object is too dense to float. So if we have a 1 cubic meter block of solid steel, which we know is going to sink in water, we can figure out that its mass will be 8,050 kilograms, and it'll have a weight on the Earth of about 79,000 newtons. If we drop it in the water, it sinks to the bottom. If we want to lift it out of the water, we don't have to apply 79,000 newtons to lift it. We've got the buoyant force working with us, and we can figure out how that changes things. So we've got the applied force that we're going to use to lift it up, the buoyant force, which is also trying to lift it, and its weight, which is trying to bring it to the bottom. And we don't have to lift it with any acceleration, so we can set A equals 0. So the applied force has to be weight minus buoyant force. Buoyant force is density of the water it's in times g times the volume submerged, which in this case is the total volume. We do the math and we get 69,200 newtons, so it's significantly easier to lift the block when it's underwater